Okay, so today it's going to be a really short lecture. We're going to basically just talk about the bonus lab, so that way you guys have time to study for the final exam. Or if you're done studying with that, you can work on the bonus lab, get a little bit of a head start on that, maybe work on it over Thanksgiving if you feel like it. But let's just go ahead and get through this quickly today. So first off, the bonus lab, what we're going to do is kind of going to rewind us back to the first lecture that we ever did in here. We talked about some of the applications of automata in formal languages. And if you remember, we had like things like creating compilers, creating hardware devices that interpreted patterns and things like a printer, like a programming language embedded inside of a game, like Quake C was an example. Taking something that's programming language like and turning it into hardware like VHDL or Verilog based systems for programmable logic. Even something like parsing a file like for a web browser like HTML or CSS, that requires us to interpret patterns and extract those patterns and make sense of them. And all of those things are where formal languages shine. Well, one of the things that we saw was that automata and formal languages kind of concepts were used kind of across the board in every aspect of computing, from hardware to networking to programming higher level things in higher level programming languages. And one use that we had mentioned but we didn't really talk about or show much of an example of was natural language processing. And so for the bonus lab, we're going to have a little bit of fun with that natural language part of that. And automata and natural language processing, the idea there is natural language, as I'm talking, it has a certain syntactic structure for the sentences. And that essentially governs how the patterns of words are fit together and how you're listening to them, extracting meaning from those patterns of words. So you have built into your head kind of a parser that you've learned to fit the filter the sounds through, that divides it up into words and then takes those words and applies a syntactic structure. And that allows you to take the ideas that I'm thinking coming out of my mouth, going through the air, or in this case through YouTube, and then being replayed back to you, and you're putting them back together, extracting that syntactic structure, and then getting what you think the idea is that I'm trying to convey. And that is a remarkable invention from a kind of an evolutionary standpoint. It's what has allowed humans to do the things we've done. We have a way to take ideas out of one of our heads and move them into somebody else's head. And that's what the whole point of learning is, and the whole point of like speech and talking. It's a way to do that. So automata and formal languages, though, are kind of that study of patterns, of strings that represent things like languages, making machines that understand or can make sense of those things, those patterns, can parse those patterns, can verify, hey, does that pattern fit this language or does it not fit this language? But that's what automata and formal language is all about. It's kind of like the mathematics of pattern processing. And DFAs can represent regular language patterns. Context-free grammars can represent context-free language patterns. So we're going to have a little bit of fun with playing around with these things as it associates with natural language. So we're going to play with making some DFAs and some grammars that represent kind of natural language-like constructs. And then you're going to write some fun programs that kind of help illustrate that relationship. So let's take a quick look at the lab sheet here. So what I'm going to do is I'm going to switch over so you can actually see the lab sheet here. Give me 1 second. All right, so here's the lab sheet. And you'll notice the due date on that, pretty much the first day of finals week by the end of the day. As long as you have this submitted by then, everything's good. But let's take a look at that. So it basically says automata in formal languages is a subject that largely deals with the study of patterns and abstract machines that match patterns. One use of this is finding or producing patterns that exist in natural human languages such as English. And it says the NFA below is a simple finite automaton that represents a subset of grammatically correct English sentences. And this is one that I kind of threw together that kind of illustrates this ability to represent certain kinds of sentence structures, in this case with a non-deterministic finite automaton. And you'll notice as I go through this, let me scroll up just a little bit so you can see what these different categories are here. So the different categories here, noun, that makes sense. Person, place, thing that you learned. But in our case, we're just going to use this kind of subset of things. So man, woman, student, teacher, programmer, geek, nerd, genius, princess, prince, wizard, ninja, and toad. A determiner is represented by this DET here. That is something that deals with determining some quantity of things or a specific one of something. So a and the, in our case, it's just a, the, some, that, this. So you'd say like that man, that woman, a man, the teacher, some teacher. But that's what determiners do. So then we also have kind of the helping verbs, which are represented over here by this HPV thing. So is and was are the only two that I put in there. So we have this helping verb. And then we have conjunctions, a, or and, or but. And then we've got adverbs. So sometimes, often, never, always. And you could add more to these lists if you wanted to. But for right now, just make sure you have those ones in your implementation. And then we have our adjectives. Adjectives, happy, sad, good, bad, clever, lazy, brilliant, stupid, lame, useless, crazy, silly. And then pronouns. And pronouns are like names that you're used to thinking of. So we have Ted, Paul, Jason, Jim, Dwayne, Mario, Harry Potter, Gandalf, Ada, and Ron Weasley. And then end P is our end punctuation. We just have period, exclamation mark, and question mark. So if we actually follow through this NFA, following things as we go. So for example, you could have determiner, noun, followed by helping verb. So you might have the, let's say ninja, the ninja was, and then we can have adverb. So ninja was sometimes. But we could skip that adverb if we wanted to by that lambda that goes around it. So we'll just say we went through it. So sometimes a, and then adjective. And those adjective can loop back to itself, so we could have that. So the ninja was sometimes a happy, useless, and then adjective to get out of there. So happy, useless, stupid, and then noun. Geek, exclamation mark. And so basically what we're going to do here is what I want you to do is for that English sentence NFA above, we want to modify it so that it'll also accept these following sentences. Paul was sad. So that, notice that that is a pronoun followed by a helping verb followed by just an adjective. So let's see if that can do that. So Paul was, now we need just an adjective that gets us from here over to there where we have our end punctuation. And we don't have that. So we don't have just an adjective going over there. So we would need to add like an adjective transition. And actually we can get there. So Paul was lambda, lambda, sad, period. So that one actually is good on. So we'll check that one off. Now let's say Jason and Jim were sad. So that requires two pronouns in a row with, in this case, an and between them, a conjunction. Well, we don't have any way to get multiple conjunctions here. So we would have to have pronoun and then conjunction back to here. So Jason and Jim were sad, period. So what I want you to do is go through the rest of these and figure out how you would have to add transitions to this or modify this NFA to also accept these other sentences. And then what I want you to do is so you get 5 points for that. So just for taking this chart, adding the edges you need onto it. And if you want to, you could print this out or download a picture of it and just add the little transitions on here and paint or whatever. But then what you're going to do is you're going to take that and you're going to convert that NFA. So this is an NFA. Notice it has lambda transitions. In some places it has edges, multiply defined edges with the same transition label leaving the same state. So you're going to turn this NFA into a DFA. And then that's worth 5 points. And then once you have that DFA, then you're going to write a program that chooses a random walk through the DFA And as it goes, it's going to randomly choose tokens from the correct category for each edge that's traversed. And it's going to essentially create these randomly generated grammatically correct sentences. So you're going to write a program that then repeats that 100 times, and you get 100 of those. So you'll get things like Ron Weasley was sometimes a happy woman, and Harry Potter was never mad. Paul is a nerd, but Jim is a magical, silly wizard. So you'll get things like that pop out of this. And the way you're going to write the code is you just have a state, and you look at, okay, well, what are the edges that leave that state? So you start in Q0, that's the start state. So determiner leaves that and goes to Q1. So you say, okay, well, let's take that path. Now we're in Q1. What are the edges that leave Q1? Just a noun. Take that one. Now we're in Q2. There's only one edge that leaves that. Let's take it. Helping verb. This one, in this case, has one edge leaving it. Well, actually more than one once you turn it into a DFA, because you could also be here. You could also be there. So you're going to have, what, 1, 2, 3, 4, 5 edges leaving that one. But you're just going to take a random walk through that graph, and eventually you'll end up at this end punctuation. And when you do, that's the end of the road, and you print out that sentence. Okay, now for part 3, so that's using kind of a DFA kind of construct to represent, or a finite state machine to represent the kind of thing that we're talking about with natural language. And the second part of this, or part 3 of this, is we're going to, or actually part 4 of this, sorry. Part 4, you're going to do the same kind of thing, but we're going to use this, we're going to use a context-free grammar to do that. And so in this case, you're going to write a function that uses the context-free grammar, this context-free grammar here, to generate random sentences in the language defined by the grammar. Now, how do you do that? Well, you start with S, and then you replace S with these variables, and then those variables, so here's, for example, NP is noun phrase. So you take NP, and then you replace that with the right-hand side. Now, if there's a choice in right-hand sides, like where there's this or, then you randomly, like here for verb phrase, there's 3 possibilities. It's either just a verb, or a verb followed by an adverb, or a verb followed by a conjunction followed by another verb phrase. So what we do is if there's more than one choice on the right-hand side, we randomly pick one of those and then expand it to that. And then we keep doing that, taking a variable, expanding it, variable, expanding it, variable, expanding it, until we have a string of only terminals. And when we do, that's a sentence that's in that language that's defined by this context-free grammar. So in this case, it's kind of a similar thing, but you're expanding this. So what I want you to do is just generate 100 of those randomly generated sentences of what I call crappy poetic phrases. And so some of the ones that my program generated, these beautiful, lonely, colorless winds sleep slowly. That pops out of this grammatical structure up here. The beautiful moons disappear woefully. Many beautiful ideas die woefully and disappear slowly. The painful, painful winds disappear. A lot of things disappearing slowly here in the examples anyway. Many yellow sighs wither selflessly. Some lonely yellow winds decay. Unhappy face. And so basically just turn in your programs for part 4, for part 3. And then for part 2, you're going to turn in kind of your DFA graph that you created. That could just be the table for the DFA that was created from the NFA conversion. And for part 1, you're going to turn in the NFA. It's going to look like this, but with some extra edges added and maybe some modifications to it. All right, so that's it. So let's go back to the presentation for just a second here. All right, so we looked at the lab sheet. Really, that's all that we're going to do for today. You can work on that. I would also suggest that you check out the study guide, be ready for the final exam next week. And you can work on that bonus lab. The bonus lab, that stuff isn't really going to be on the, obviously converting from an NFA to a DFA, things like that. Working with context for grammars is going to be on the final. But if I were to suggest to focus on one thing right now, focus on the study guide, making sure you understand that. Focus on the stuff to be ready for the final exam. And then if you have some free time or you feel pretty confident in that, go ahead and work on the bonus lab, because that's worth 30 points on your lab grade. So if you had some quizzes you didn't do well on, or some things where you missed some points here and there, then, or you just aren't as confident, or you didn't do as well in the midterm as you wanted to, those bonus points can make a huge difference in your grade, especially with 30 of them. sitting there, and those programs are actually pretty fun to write. It's actually a lot of fun to play with those. And if you feel like it, after you turn that in, change the grammar around, add different things to it, add some words to it. It's actually a lot of fun to play with it. There's actually a famous book that's that was written that was entirely computer-generated poetry that was generated in that same kind of methodology. And so if you're interested, computer-generated poetry is kind of a fun thing, but it's all kind of built around automata and formal languages. And also, when you're using a device like the Alexa and you're talking to it and asking it questions, it's got to figure out what you're trying to ask it based on the sentence structure that you used. And so that is all based on automata and formal language kind of things as well. So think about that when you're saying, hey, Alexa, can you please set an alarm that does this? That sentence structure, how it interprets that and extracts meaning from that, it's not the same as what we're doing in this lab. We're going the other way. We're taking the grammar or the DFA and then producing a sentence from that, where Alexa's taking the sentence and then parsing it based on some set of rules similar to what we have there. And that's the kind of thing that, again, automata and formal languages are kind of like the math and science of patterns, which is why it's really useful for computer science and programming and implementing things, because there can be patterns in hardware, there can be patterns in files and data, there can be patterns. It's also used in computational genomics. It's used in a ton of different stuff, data mining, tons of places where this stuff is useful. So that's it for today. Everybody stay safe, and I will see you in class for the final exam next week. And if you have any questions on anything, let me know. Other than that, that's it for today.